Today we will talk about chapter 4 of Aerodynamics, devoted to incompressible flow over airfoils. I think this class could be shorter than usual classes. Let's see how it goes, because today we have many problems in the news you can find, and this creates many difficulties to concentrate and to focus on subject of aerodynamics. Okay, incompressible flow over airfoils is talking about models of calculation of airfoils theories, allowing us to solve flow airfoils analytically or by simple numerical methods. It's important because we need to design an efficient profile of an airfoil bidimensional structure. Okay. Here we can see several examples. They are examples built on first part of previous century, starting from Wright brothers, quite simple geometries, and then you can see through the years significant improvement of geometries and the creation of different types of airfoils. Why different airfoils exist in modern aerodynamics? Main reason of this is because airfoils operate in different conditions and built for different applications. There is no universal airfoil that would work perfectly in all types of flow, in all conditions, for all applications or velocities. Also, we can consider not just aerodynamic point of view, like lift to drag ratio, but we can consider also structural point of view, that airfoils have limitation by its size, by its geometry perfectness, by structural strength of the wing built by this airfoil. So all these limitations result in a big number of criteria aside of aerodynamic efficiency and result in different designs of airfoils. Main reason to design airfoil is to improve its performance, so-called lift to drag ratio. We remember that there is L to D ratio, relation between force of lift and force of drag, or relation between weight of airplane and the thrust of airplane's engine. Okay, there are different types of airfoils, as I told you. Nowadays, I think there are several hundreds or maybe thousands of airfoil geometries, and they are still being developed nowadays with the modern numerical methods mostly, and also these designs are proven by experimental testing. First of all, it happens because it is still a possibility to increase efficiency, lift to drag ratio. There is still a possibility to increase performance and improve also momentum, coefficient distribution of forces over this airfoil for critical applications. Which are critical applications? First of all, people would like to fly as fast as possible. This is why must be created special type of airfoil called supercritical airfoils. The supercritical airfoils allow to fly very close to speed of sound. Special shape of airfoil allowing us to decrease separation region and to decrease strength of shock waves created on such airfoil. These airfoils are having also this smooth shape, not a sharp shape. Another reason why new airfoils are created are called low velocity efficient planners. Such planners require airfoils called laminar airfoils. Laminar airfoil is having mostly laminar boundary layer over its surface, and inside laminar boundary layer you remember that the velocity gradient is significantly smaller than for turbulent flow, so the drag associated to friction is significantly smaller than for conventional airfoils. Laminar airfoils, they also can be designed only by numerical methods nowadays, because many optimization techniques required. It's not possible to test all configurations of such airfoils. So here we can see two cases. Figure 2 is a laminar airfoil, which has significantly reduced drag and very high lift to drag ratio. These laminar airfoils, they are mostly used for low velocity flight. And supercritical airfoil is having completely different shape, is very good for flight near critical Mach number, which is close to Mach 1. Also, another aspect nowadays also important are so-called supersonic airfoils. Supersonic airfoils allowing to create aerodynamic body flying with supersonic velocities. Maybe you've heard recently there is a project of creation of so-called quiet supersonic airplane, and this quiet supersonic airplane is having very light shock waves, which do not produce so much noise as conventional supersonic airplanes. So such an airplane could be used near cities, flying with the velocity of supersonic jet airplane. So application is very important. Then if we go from airfoil to a wing, we see that airfoil is just a cross-section of the wing. Of course, a real wing is more complex than just airfoil. It might have also additional elements to control lift and to control drag. There are flaps, and we will see them in next discussions. And also the wing can be composed by several airfoils, different airfoils. For example, main section is composed by laminar low lift to drag ratio, and the second part of the wing is composed by another airfoil, different airfoil, which, for example, has a good maneuverability characteristics, right? That is responsive for control. There are also another techniques used to improve efficiency and structural strengths of the wing, but we will not touch here. Maybe you can touch, maybe you can discuss them in gas dynamics, or can discuss in future courses related to aero and gas dynamics. Okay, figure 8 showing to us dimension or typical dimensions and typical definitions on airfoil. They are main one chord side, so it's a distance between leading edge and trailing edge, where leading edge is the front part of airfoil and trailing edge is the final point of airfoil, which, as you already know. There is a thickness. Thickness is a distance between upper and lower side, maximum distance between upper and lower side of airfoil. There is a camber. You can see this camber as a distance between chord and central line or mean camber line. of airfoil, this mean camber line is in the middle between upper and lower side of an airfoil. So these parameters can describe us more or less main characteristics of airfoil. Some of these parameters could be coded inside airfoil nomenclature. Some other airfoil nomenclature, like 5-6 digit, are not having direct relation with all geometrical parameters. They have a relation with some geometrical parameters, and they also can include the lift to drag ratio or momentum coefficient at specific point, or having just a number of an airfoil, for example, developed by companies having just a number in the catalog. Okay. For 4-digit airfoil, you already know that people who chose, for example, 4-digit airfoil, there are numbers describing two parameters: a curvature of a camber line or position of a camber line, 2 fourth digits, and the thickness of the airfoil second digits. For example, these airfoils here, 2412 and 0012, they both have same 12 at the end. It means 12% thickness of cord. So we see that this thickness is defined inside number. And 24 is saying to us where is maximum thickness of the airfoil. Sorry, just a moment. I need to turn off sound on my cell phone. Okay, and 00 on airfoil 0012 says that it's 0 size of a camber line. It means that camber line is same as a cord line. In such a case, airfoil is symmetric. So airfoils with 00, 4-digit airfoils with 00, the first 2 digits are always symmetric. So it says as symmetric. Symmetric airfoils are very useful for many applications. Cambered airfoils are used for another applications. For example, cambered airfoil 2412 is having a very nice lift to drag ratio. They are quite efficient because it's not symmetric curved airfoil. But NACA 0012 is also very important because it's commonly used in control, because depending on inclination of such airfoil, lift coefficient is changing proportionally to angle of inclination. So it's a linear characteristic, very important for control mechanisms. We know that, for example, we incline 1 degree, we receive some value of lift, right? But if we need to double lift, we incline 2 times more. For example, 2 degrees, we have double lift. So it's extremely useful for prediction models and control algorithms inside airplanes or other aerodynamic structures. Symmetric airfoils are quite nice, and they are widely used for tails, for example, or for mechanisms which require a definitive value of lift with respect to angle of attack, where not symmetric airfoils are very good for creation of lift and very good for lift to drag ratio. So depend what we need, we choose our airfoil. 4-digit airfoils were created long time ago, very long time ago, right? And then we created 5-digit airfoil, 6-digit airfoil, and nowadays there are airfoils built by companies. More and more perfect airfoils for some specific applications. There are many airfoils currently used in the modern airplanes. We are not disclosed, so shape of an airfoil can be a commercial secret of a company. For example, because company use a lot of money to design airfoil, to test, to certify, to validate. So new modern airfoil, especially supercritical and laminar airfoils, they are not always available in their coordinates or precise coordinates, because it costs a lot to develop such perfect shapes. But I think one day all will be known, right? Because science is going forward, and all the results, they are not so relevant with respect to newly obtained more perfect designs. I would like to remind you that you could ask questions in case you have some questions. Please do not forget to ask them. In chapter 4, we are going through the following structures you can see on the screen. In general, we are talking about incompressible flow over airfoils, airfoil nomenclature, which we just discussed or discussing, airfoil characteristics, typical experimental data, probably data we already had seen before, you used in your work 1. By the way, I'm grateful that many people submit on time, like on schedule, work 1, and I will try to check your works probably on these holidays. During this beginning of next week, I will try to check and to give you marks, my response, so you will be capable or to improve your current report or to use these suggestions in work 2 and work 3. Okay, I will try to do it soon, but all will depend on many factors, and I would like to sorry if I cannot check fast enough, because many things are coming to us and they reduce our performance or make us working on very different aspects. For example, in this week we have 3 major events happen that significantly reduced our general performance. They are started war of Russia against Ukraine. They are new call for rocket missions that our course, our laboratory would like to participate. So we are having a lot of work related to this. And also there are some internal changes inside university which occupy a lot of time on the meetings. I mean, significant changes inside university due to current political situation in Brazil. It should not worry you, but since it is my problem, I can delay in evaluation your work. So indirectly, it also affects you. And so I'm sorry about that, but I cannot do anything with these 3 things, which one of which is good and 2 are very, very bad. Okay, please let me know if you have some questions in comments, and I will try to answer. After discussing experimental data on airfoil characteristics, will be distribution over airfoil surface of singularity. This is a problem of solution of equation system. Pure solution of equation system is not possible. We need to update or to improve our system of equations to real flow around airfoil, and for this we will have Kutta condition. For this we will have Kelvin's theorem and starting vortex concept, and this will allow us to obtain real, let's say, flow distribution around airfoil that corresponds to real flow. Okay, but the problem is that if you try to describe all by mathematical model. Mathematical model purely is very different from real life. So you need to adapt your mathematical model to some physical process that happens in real life. So this model will correspond to a physical process in global or globally. Okay. Also, to solve this question of mathematical modeling of flow, I will present you a concept of a vortex sheet. It's a concept similar to a panel method, which we discussed on our previous lecture. But here, instead of source or sink on distributed on a line, we will use a vortex distributed over the line. Okay, and then applying to airfoil, we have two different models. General one, which is calculation of airfoils of arbitrary shape, most general model to calculate airfoils and obtain lift analytically and numerically. It's mostly numerical method, because shape of real airfoil can be described point by point. Shape of real airfoil, complex airfoil, cannot be described by a simple continuous function. You already know that shape is described by point, for example, according to data you had in work one, right? Many points needed to describe airfoil, not one function. Simple airfoils, of course, they can be described by one function or approximated by one function, but it's not a general case. And as a consequence or a particular solution of this general model, we will have a model called classical thin airfoil theory. That is simplified numerical method, allowing us to calculate two types of airfoil. Symmetric airfoil, which is simple, right? Because upper part is equivalent to lower part, so we can calculate just a part. And the cambered airfoil as advanced calculation with respect to symmetric airfoil, which will take into account not just size and thickness, but also curvature of this airfoil. And according to curvature of airfoil, we will see how can be calculated aerodynamic characteristics of this structure. And then we talk about airfoil drag, which does not enter in numerical methods. We will see how airfoil drag, what concepts could be used to estimate airfoil drag by analysis, let's say analysis, numerical analysis or experimental analysis. So this was a roadmap for chapter 4. Okay. I see no questions for now. I will continue. Airfoil characteristics, next topic. You saw this already in partial, we already discussed, just reminding you because we have to deal very soon with the model. So just reminding about these characteristics that presented in figure 4.9, lift coefficient with respect to angle of attack for airfoil, which is composed by two parts. Part one, it looks like a line, a linear function. Right? You see, I put line on this screen, and it perfectly attends my first part of function, and it's a lift coefficient. And the second part is curved. Okay, can be this shape. Okay, it has different shapes. as different shapes for different airfoils, and not just for different airfoils, but even for same airfoil with different conditions. For example, for different Reynolds number, for different Mach number, this part of curvature can change. First part, linear one, can be described by lift slope. Lift slope is a derivative of lift coefficient by angle of attack, is just one parameter. It can be calculated as a function, as you see here, or it can be calculated just as one value when you know two values of angle of attack and lift coefficient corresponding to these values. You can calculate A0 approximately as delta CL divided by delta alpha. This is delta alpha. Okay. And this is delta CL. Very simple way, right? Since it's a linear function, we can take any two arbitrary points and obtain. Of course, as bigger distance we have between these points, more accurate is the result. But we just need to stay inside the linear part, linear region. So that's simple. And then chord region corresponds to flow separation. Starting from this point I mark on my screen, flow separation happens, and this region of flow separation is shown on the right part of the screen, is characterized by some volume where we have recirculation, quite active recirculation, intensive recirculation of air, and with increase of angle of attack, this recirculation zone grows, becomes bigger and bigger. So, and because of this, lift coefficient goes down. So our effective work of airfoil happens until its maximum point. Right? We would like to work until maximum value, CL maximum, which corresponds to, you remember what, right? Stall angle of attack. It's and stall velocity is the minimal velocity at which airplane can take off. Very important to design and to know this value to design landing distance or airport. Okay, and then there are also other characteristics. For example, lift coefficient and zero angle of attack. It corresponds to Vmax, maximum velocity of flight. So somewhere near this zone, we also see maximum of lift to drag ratio. So this point exactly corresponds to maximum velocity. So it's usually happens on small positive angle of attack, small positive or zero angle of attack, and it has positive value of lift coefficient. And with respect to drag, it's most efficient point of flight, and we can reach maximum possible velocity of flight for this airfoil. There is also a point of alpha L0. It's usually a negative value of angle of attack when lift coefficient is equal 0. And when you continue to decrease lift coefficient, it will continue to go linearly, and then will be curved in the same way as positive angle of attack, and also will happen due to flow separation. Okay, this curve is not purely symmetric; it's displaced with respect to origin of coordinates or axis alpha or axis CL, but more or less you can find the same behavior of lift coefficient in a negative direction for negative angles of attack. Okay, so this is, I think these are the most the most comments about these curves. Here we might find some examples. They are related to NACA 2412 airfoil. It's an old airfoil, cambered one, and not symmetric, of course. And you can find the experimental distribution of lift coefficient on the left side, and experimental distribution of momentum coefficient also on the left side. And also a line corresponding to equation 457, which describes lift coefficient, and a line corresponding to equation 464 describing momentum coefficient. It means that very soon we will be capable to elaborate equations which with a good precision describe such an airfoil analytically, right? Or equation means that we have an analytical model for such airfoil, and we can use this analytical model to predict lift coefficient and momentum coefficient in such non-symmetric cambered airfoil. So it's an advantage, right? Very soon we will see how to calculate any airfoil analytically, at least their lift coefficient and momentum coefficient with respect to angle of attack. This is an advantage, very big advantage, right? We can predict calculation, we can predict performance, not performance, sorry, lift coefficient, at least this force. But unfortunately, looking on the right side of the screen and looking on drag coefficient, we see that there is no line and there is no curve. So there is no equation describing distribution of drag coefficient. It means that nowadays, and theoretically also not possible to find analytical function describing, sorry, I have some sound from outside. It should not disturb you. Please let me know if this sound from outside is loud. I could stop for a moment until it stops. Until
no, it's quite enough.
Yeah, okay. It's okay?
Yes,
Yeah,
yes,
it's okay.
Thanks. Oh, because these people are selling stuff outside. Sorry. So there is no function describing to us drag distribution of drag. We will never find it in any book analytical function like this. Okay, can be a processing of experimental data converted into a function, empirical function, but unfortunately just processing of data can give us these results, not any pure analytical method allowing to calculate drag coefficient as a function. So this must be very, very clear to understand that analytical methods are not so powerful and not possible to use for all cases, especially in case of drag, because drag in case of airfoil is mostly formed by viscosity and boundary layer, a flow interacting through boundary layer with airfoil, and such interaction is so complex that not possible to describe by any analytical formula. Find solution. I mean, we can describe by formula, which is, for example, Navier-Stokes equation with an appropriate turbulence or laminar model. But unfortunately, you know, this model cannot be solved analytically, so we cannot visualize here in on these graphics. But for lift coefficient, we can do it because lift coefficient is mostly created by pressure distribution, and pressure distribution can be easily calculated through Bernoulli equation and through Laplace equation, as we saw previously, right? So pressure we can calculate, so it means that we can elaborate lift coefficient for airfoils, and momentum coefficient also, because momentum coefficient depends on lift, right? You remember that lift multiplied by distance will give us momentum coefficient. Okay, multiplied by some other coefficient, linear one. will give us momentum coefficient. So lift coefficient and momentum coefficient are correlated. You can obtain one from another. But drag coefficient is so difficult to describe that we cannot find an analytical solution. It's very important to remember, so do not forget that we have at least a possibility to calculate lift coefficient for any airfoil. And for example, if you use program called Xfoil, this is done in science software, and model used to calculate it we will discuss right now. First of all, to start talking about how to calculate lift around arbitrary airfoil, we need to present a new concept called vortex sheet. This vortex sheet is a vortex distributed on the line, along the line. You can see figure 13, this right part of figure 13 is a line on which vortex is distributed. It's a continuous function which describes a vortex function over the line. This line from A to B probably goes according to shape of the airfoil. Sorry. So we will have distribution of vortex. But since we are talking also about lift, we need to calculate this force in a three-dimensional case. So our vortex will not be just simple bidimensional vortex. It will be a vortex in 3D space where Z coordinate goes from -infinity and to infinity. So it will be infinitely long vortex sheet. So I hope that you understand that vortex sheet is something real. Real vortex cannot be infinite, but just for mathematical calculation, we need to extend this vortex sheet in a third dimension, because according to several theorems in mathematics and in physics, vortexes cannot start and stop. They just go. They can finish on the wall of a body, or they can go to infinity. We'll see it soon. So this is again figure 13, which we had before on the previous slide, and here equation 1, 2, and 3 describing potential function for this vortex sheet. What does it mean, this potential function? We, first of all, in equation 1, see velocity differential. We see that velocity in any arbitrary point P is changing, dV, according to presence of vortex on each segment, infinitely small segment of this sheet with strength gamma, and the size of this segment ds. And this change of velocity in arbitrary point P happens reverse proportionally to 2 pi and distance r. So longer is our point, or more distant is our point from a point we are calculating on the vortex sheet, or we are accounting on vortex sheet, smaller will be contribution to dV according to this hyperbolic function dV. Okay, for example, 1 meter and 2 meters. If we 2 meters more distant from 2 times more distant from this vortex, our change of velocity will be 2 times smaller than before. So, and then it goes according to this hyperbolic function. And we can see that if point P is placed on infinitely far distance from vortex sheet, dV will not happen. or change of velocity will not happen. This corresponds to infinite conditions. Infinite conditions, V infinite, because V infinite is undisturbed flow. It's not important how big is strength of this vortex, how big is the size of this sheet of vortexes, but change of velocity will be 0, and it guarantees to us that on external wall of calculation or on infinite distance from airfoil, velocity will continue to be infinite velocity undisturbed. I see one question, please let me read. It is right to approach drag coefficient to a polynomial functions using numerical methods as the least squares method, for example. As I told you, that of course you can process experimental data. This experimental data can be received from wind tunnel or experimental data received from numerical simulation. You can process these functions, but these functions, for example, as parabolic functions, they will not be purely analytical solution. They will be just a result of processing of discrete data points. They will be so-called empirical functions. Okay? Empirical functions is processing of other results, but analytical result is pure application of flow equations and solution from flow equations. They are not going through, they do not have any relation to experimental data. And then you say that I know that I have to know some points, but there is a way to estimate the drag in other angles of attack knowing some experimental data. It's a very tricky question. When and how many points you need to estimate drag, how many points you need. Because we know that drag distribution for any airfoil is very similar to this we can see on this picture on the right side of my screen, and it's close to something similar to parabolic function or polynomial function. Then we can predict that it will go in many cases close to this distribution, right? So we need an additional knowledge how this function will behave. And this knowledge we take analyzing similar airfoils like this. Okay, we already see that for NACA 2412, function looks parabolic. So I expect that for airfoils similar to this, also we will have parabolic behavior of drag coefficient. It's extremely important because you will need to choose shape of approximation function. Approximation function is the function which you use for this case. For example, here just guessing how much could be the CD. This okay. Let's try to write CD is some coefficient A, which coefficient which corresponds to CD0. Okay, I can also write this CD0, drag coefficient at 0 angle of attack, and then plus alpha multiplied by some coefficient, linear coefficient, and plus some alpha in square multiplied by another linear coefficient. Probably like this will look this curve here. So we can guess about shape, but it's not analytical. We cannot call it analytical solution because it's purely analysis of data. How many points you need to know? You need to know as much as possible. As much as possible. For example, if you know just 2 points, initial point and final point, and point in the middle, you can try to approximate with function I wrote you here. 3 points, 3 unknown coefficients, CD, A, and B. Okay, so to find these 3 coefficients, you need 3 points. If you have, for example, 4 experimental points, some point in the middle, you can put one more parameter here, for example, plus C divided by alpha, or something which fits inside this logic here. So you will find another coefficient if you have 4 points. If you have 5 points, you can extend your function to make, for example, function of third order. Okay, and etc. etc. In any case, is different from another cases. Okay, I can write here instead of C divided by alpha, another example, C multiplied by alpha cubic. Okay, if we have 4 points and 5 points, we can put more functions, 6 points. Not important to put a huge long function. Probably you can have 10 points, but have just 3 coefficients. In such case, you will use a method of least squares to optimize coefficients CD0, A, B, and B. So least square coefficients, as you mentioned, right? When number of points is bigger than number of coefficients, we can use least square method to optimize, as you know from some other subject, probably numerical methods, right? Where you can work with this function, of course, inside interval of your data. For example, this is my minimal value of alpha minimum, and this is my maximum, alpha maximum. And I have points in the middle between alpha minimum and alpha maximum. So I can use these functions just in the middle. I cannot use for other values on the left, unfortunately, because I don't know where this function will go. Maybe this function go this way, maybe this function go this way, or this function goes this way. It's okay, it cannot go backward, but in this way. So there is a huge unknown problem, or let's say it's a divergence we might see, which will not allow us to extrapolate data. Extrapolation is a very bad idea in aerodynamics. Extrapolation is probably the worst thing you can do in aerodynamics, because function can go in completely different way as you expect. So I recommend you, if you use such approximation methods, to work inside the region where you know data. If you know limits, you have points in the middle, you can use this function with no problem, right? No problem, I mean no huge problem, because definitely your function will not do something like this, will not have a local extremum, because here we do not have any experimental data, so it will not go like this. This function is having its minimum in the middle and has 2 extremums in negative and positive angles of attack, right? It has 1 minimum and two maximum values. It's predicted. It's not something unknown. So I recommend you to use in the middle. And this is especially for drag coefficient. For other coefficients, for example, moment coefficients, this is not applied. Not applied. Because depending on Reynolds number and angle of attack, you can find completely different behavior of momentum coefficients. It's a combination of influence of lift and drag. When you have inclined airfoils, you might find very different behavior with respect to different Reynolds numbers. So for momentum coefficient, if you can analyze as many points as possible for experimental data and work in between points, like a linear approximation would be the best, probably. My opinion is the following. Linear approximation is always the best, because if you have polynomial function of second order, it has at least 1 extremum. If you have a polynomial function of third order, like you can see here, it already will have 2 extremums. So it means that it's somewhere it will curve again like this. Okay, I will just leave you this. So one extremum is real extremum, which we have according to experimental data, but second extremum will never happen because because of mathematical model we are using to describe this function. So must be very careful to apply this parabolic function, especially of more than second order, because having more than one extremum, you can find this extremum exactly in the middle of your region of your work, and this will destroy completely analysis of aerodynamic characteristics. So because of this, I say linear approximation just with the functions without square, just CD0 plus alpha A for each region would be the best option, because it never will lead you to overestimation or big underestimation of aerodynamic coefficient. It will always give you something in the middle. Of course, it's not perfectly fitting the curve, but you will not mistake significantly as in case of parabolic approximations. Okay, each case is different. Be very careful choosing the function. If you have doubts, please ask. I'm always ready to answer, to suggest. I hope it will be one more opinion is better than nothing, right? So I'm ready to help if when you need. Let's go back to. Please tell me what, Pedro.
Yes, thank you.
Okay, you are welcome. Sorry, I need to drink some water from time to time, because it's when you speak too much, it's not easy. So we obtain equation 1, which is change of velocity in any arbitrary point proportional to strength of vortex at each specific point, distance where this vortex is working, and the reverse proportional to 2 pi coefficient and r distance from this specific point to a point where we are looking velocity change. Then when we integrate left and right side, on the left side we will find the potential function, differential, and on the right side we will find the integral value. We already had this, how to say, potential function for vortex, and you saw that potential function for vortex is proportional to vortex strength, reverse proportional to 2 pi, and proportional to theta, which is angle in polar coordinates. And then, since equation 2 is still remaining differential, we integrate one more time and receive a potential function. So we can say that potential function created by vortex sheet would be coefficient 1 minus 1 divided by 2 pi multiplied by integral from beginning to the end of this line, multiplied by theta and multiplied by strength of vortex in each point. Gamma is a function from A to B. It's not constant value. So it's inside integral. And theta is also inside integral because it's also a function from A to B. Theta is changing. For example, if I choose in some initial part gamma, okay, this would be my R, and theta would be different as well. Okay, so R and theta are changing, and this is why they are inside integration. They cannot be outside, as 1 divided by 2 pi is constant. Once we integrate all these, we find distribution of our potential function in space xy or xz, such as here. It's not important how you call axis, right? Or can be a distribution of potential function in polar coordinates. also can be transformed to polar coordinates. And after, if we want to obtain velocity components, we just need to take a derivative of potential function by x and y, or in such case, x and z coordinate. For example, u component of velocity would be d phi by dx, and w component of velocity will be d phi by dz. Okay, since we have not y component by z component of direction, I name this velocity as w component of velocity. V component of velocity is equal to 0, I assume. Okay, because it goes from minus infinity to infinity in y direction, so this is why. And then big velocity vector would be square root of u in square plus w in square. This is how we obtain velocity from analytically calculated potential function. And to obtain pressure, we use Bernoulli equation, which relates velocity and pressure. So from when we know velocity, we calculate pressure. This is it. And then pressure enters inside CP coefficient, inside calculation of lift. And I think already we saw these equations before, and soon we will see again. So no need to write right here. So we need to solve this integral, and we obtain potential function. All other parameters from potential function could be calculated. There are some unknown, as you understood. It's not a complete system of equations, right? Just an example how potential function can be calculated in arbitrary vortex sheet, in arbitrary case. Now we will try to apply this information to calculate a real airfoil. Before this, Anderson also proposes us to find relation between circulation and velocity change, or tangential velocity jump. It's presented here, figure 14, tangential velocity jump across a vortex sheet. We have a model, or let's say, not a model, but a control volume, rectangular one, and the vortex sheet in the middle. We have velocity changed due to presence of this vortex. Two velocities are different. U1 on the top of control volume and U2 on the bottom of control volume are changing. And we have two velocities which are constant. V1 and V2 are constant. There is no influence on V1 and V2 because vortex is acting. Vortex is long in horizontal direction and has a very tiny space in the vertical direction, so does not disturb in vertical direction, just changes horizontal component of velocity. This is a simplification. Okay, in real flow, of course, this doesn't happen, but to find analytical model, we need to have some assumptions. And this is one of assumptions, that our vortex or our airfoil is long with respect to size, thickness, or thickness or curvature of a camber line, or thickness, whatever. Then writing definition of circulation, which is integral of velocity over closed space, or as we found already, integral of gamma over this this line. Analytically, since this line is infinitely small, infinitely short, has size ds, this integral could be converted to just product of gamma multiplied by ds. On infinitely small distance, gamma stays constant. and ds is the size. And so circulation is a product of strength of vortex multiplied by size in horizontal direction. Applying this definition of gamma calculation, gamma big gamma, capital gamma calculation, to our control volume, we can find the following formula here, and then we can simplify this formula according to an idea that in the vertical direction V1 and V2 would be negligible with respect to horizontal velocity values, negligibly small V1 and V2, so it's excluded. And we have just gamma ds is equal to difference of velocity multiplied by ds. This ds and ds we can cancel from left and right side. And we result in the following conclusion that strength of infinitely small vortex on the airfoil would be equal to difference of velocities between upper and lower side of this airfoil. It's extremely important conclusion. This definition could be applied to any structure of aerodynamics where curvature of this airfoil or curvature of shape is not big with respect to size of body. For highly curved shapes, of course, such definition cannot be applied. Hope it's clear. And now, since we have already all these elements of our model, we can elaborate flow over arbitrary airfoil or model for this flow. Let's see general case, figure 15. On this figure 15, we see an airfoil, arbitrary airfoil, and thickness also relatively big, right? It's exaggerated, okay. And we can see that gamma circulation over this airfoil can be calculated by already known integral function, right? There's nothing new here. And at the same time, this gamma has straight relation with lift of arbitrary airfoil. Bigger is circulation, bigger is lift proportion. This proportion we already called in our previous lecture as a Kutta-Joukowski theorem, one of the most fundamental definitions in aerodynamics. Kutta-Joukowski theorem giving relation between lift and circulation over airfoil, or not just airfoil, but any arbitrary body, any arbitrary aerodynamic body. This relation will work. It means when we know circulation, when we analyze velocity field around airfoil, when we know density and velocity on infinite distance, not on airfoil, we can calculate which lift is created by this body. So analyzing flow around, we calculate force on this body. Very nice, all right? This is in general. But what is the problem for this model, this two-equation model? The problem is that, unfortunately, gamma can be any function that satisfies second equation, any function. And we cannot have any function describing our gamma. For example, integral will be, let's assume this integral would be equal 1 unit. Okay, 1 unit. So it means that if we put here 1 unit, we receive our lift for some function. Okay, but this integral can be received for many different functions. For example, I have here is my S distance on the airfoil, and here is my gamma distribution. I have, for example, this distribution like a step function, right? This is all my airfoils finishing here. So I have step function and I calculate integral, it will be equal 1. But I can find infinite number of such functions where integral will be equal 1. For example, function similar to this. Also, we'll have area or integral equal 1 because, okay, say we'll have same area, or any other function. For example, such hyperbolic function or linear function. So I can find the infinite number of possibilities to satisfy these two equations. But in real case, I do not have infinite distributions of parameters around my airfoil. I have a specific distribution of parameters around my airfoil that correspond to real velocity distribution and real pressure distribution around my airfoil. So solution is just one. But according to these two equations, we can find infinite number of solutions. So we need an additional definitions, restrictions to solve these equation systems and to find this unique solution for our flow. I think it's more or less clear that in case of, as it's written on the top of the screen, we cannot receive just one solution. We can receive as many as we want, but we'll never find correct one just with these two equations. So let's try to restrict model and find correct solution for gamma. One way to make it possible is already approach starting on figure 14. This approach is a simplified figure 15 when we consider our airfoil thin. What is thin airfoil? Thin airfoil is some airfoil that is thickness is small with respect to its length. For example, if I write thickness as T divided by length is chord C, could be some value, right? Thickness by chord multiplied by 100%. It's our agreement, let's say, it's an agreement, which airfoil to consider thin airfoil, which airfoil to consider thick airfoil. Many people agree that thin airfoil is an airfoil which has at most 12% of thickness. So maximum should be smaller or equal than 12%. If thickness of this airfoil T is smaller than 20% of length, then airfoil can be considered as thin airfoil, fino, airfoil fino. So for thin airfoil, if we see from a long distance, let me try to imagine long distance, we see almost same line on the top and on the bottom. Okay. More far from airfoil, more closer are two lines, upper and lower line edge wall. So upper and lower wall close one to another. Thin airfoil theory has the following assumption that upper and lower line of airfoil is the same line, is absolutely same line, and is described by a middle line between top and bottom. Sorry, I will try to make a middle line, but I am not sure I can do it by hand. So middle line, just exactly in the middle, it's called camber line, right? The definition we already had. So this camber line represents our airfoil, not surface, not upper and lower surface, but just a curvature of thin airfoil is already enough to describe all this airfoil, and we neglect existence of its thickness. So this thin airfoil is converted to a single line on a vortex distributed over this line. This is a significant simplification, right, with respect to picture on the top. Because we have just one line. We have no more wall. We have just a central line and one vortex. And this is a significant simplification, because in such case we can find analytical solution of that equation of gamma distribution. Another important, not simplification, but additional point to the model of calculation is so-called Kutta condition. There are two contributions of German scientist Kutta in science. There is a method of Runge-Kutta, right? There is a Kutta condition, which is different, right? Condition. And the third one we can Kutta theorem also. But okay, I think everyone knows what is a method of Runge-Kutta, because you use it in a solution of ordinary differential equations, right? I hope you study in numerical methods. Here we study other thing, which is Kutta condition. What is Kutta condition? Let's observe case left and right. Real flow can happen only in case 2. Real flow will never happen in case 1. It's not possible physically to have such a flow picture where 2 stagnation points are placed on the top and on the bottom of an airfoil. This flow will never happen, but if we solve Laplace's equation, we can find this numerical solution case 1, and also we can find numerical solution case 2, depending which boundary conditions we set. We can find case 1 and case 2. Case 1 not possible. Case 2 is the real flow. In case 2, second stagnation point is placed exactly on the trailing edge of our airfoil. So Kutta condition allows us to obtain, solving numerically, stagnation point at the trailing edge of the airfoil. So this is a significant thing, that just applying Kutta conditions, we can obtain case 2. If we do not apply Kutta conditions, we will obtain wrong case 1, which is also solution of numerical methods. You know, solution depends on conditions or boundary conditions. In such case, Kutta condition is significant. What is Kutta conditions? Just in a moment we will see. This concept of stagnation point on the trailing edge of airfoil is proven experimentally, as you can see here. On each case, for different angles of attack, we can see that flow goes from trailing edge of airfoil. It does not go from any arbitrary point on the top of airfoil. So this flow does not exist. So flow from top point, from top edge of airfoil does not happen in real life, only from the trailing edge. This proves Kutta condition and existence of Kutta condition, and proves that we must always take into account this equation to obtain correct solution according to our real physical process. Kutta condition is extremely simple. We can find the Kutta condition for 2 different shapes of trailing edge. For finite angle, where these are both trailing edges of airfoil. Finite angle is when we have an angle, some value, right? This theta angle of the body on the trailing edge of airfoil. In such case, when flow goes from top and from bottom of our airfoil, it meets at same point A, and according to wall direction, it should go in two different directions at the same point. Since movement of flow is possible just in one direction, these two velocities v1 and v2 will be equal to 0. Okay, this is the only case possible when you equilibrate velocity at point 8. Velocities are equal to 0. And there is second case, which is cast, where this angle theta is 0. Okay, it's sharp. It's a sharp, extremely sharp, very small angle, or it is limited to 0. Okay, goes to 0. In such case, velocities from the top and from bottom surface of airfoil are parallel. And in such case, since they are on the same point A, they are equal. Because on the same point, you cannot have velocities of different values. On the same point, you have same velocity, right? Same velocity, same direction, and same size. So V1 is equal V2 and not equal to 0 for cast edge, and for finite angle, V1 equal V2 and is equal to 0. Both of these observations, when we apply to previous definition of gamma as a difference between velocity on the top and on the bottom on our vortex sheet, this velocity difference is a function of gamma. Tell us, since in case A, velocities are equal and equal to 0 in a finite angle case, so gamma will be always also equal to 0. And in case of B, cast angle, since this V1 is exactly same as V2, difference between them also will be equal to 0. And gamma will be also equal to 0. So in any case of any angle at the trailing edge of body, strength of vortex on the trailing edge, gamma TE, will be always equal to 0. So the final point in our numerical calculation, when we define gamma distribution over the airfoil, should say that gamma at the last point of airfoil is equal to 0. So it cannot change, cannot have a positive or negative value. It should have a 0 value. And this is called Kutta condition, which guarantee that stagnation point on the trailing edge of our airfoil will be exactly on this trailing edge. Okay, at this moment, I would like to finish. Next time we could start from this question, or maybe better to start from the next question, because a simple answer, if we could have a lift without friction, is no. You can find in Anderson book why no, because always flow is real flow is having friction, so lift is not possible, because generation of lift is a complex process of flow transformation, and real flow always is viscous. So you can find why not possible to have lift without friction. I think I can keep for your self-study. Next time we will start from Kelvin's circulation theorem and starting vortex concepts to develop a numerical method for calculation of flow with lift for specific types of airfoils, and then to generalize in arbitrary shape airfoil. Please let me know if you have some questions I can answer today. Okay, so I see no questions. Would like to thank you for participation today, and have a nice time. I hope things will become better in future. and see you soon. Thank you.